In this video, we'll look at what happens when a system at equilibrium undergoes a temperature change. Being able to solve these problems requires that you know where the heat goes within the chemical equation for the equilibrium. Do you write it as a reactant or as a product? Because when you know that, then you can treat heat as any other reactant or product that is added or removed. It makes the temperature problems much easier. So let's do a quick review of endothermic and exothermic reactions. In an endothermic reaction, heat is absorbed and delta H is positive. Because heat is absorbed, we treat it like a reactant, so we write the word heat on the reactant side of the equation. In an exothermic reaction, heat is released and delta H is negative. Because heat is released, we treat it like a product, something that is formed, and we write the word heat on the product side of the equation. Temperature is different than the other stresses we covered in the other video. When we change the temperature, we shift the equilibrium permanently for that temperature, and K will change. Temperature is the only parameter that can change the value of K. For everything else, when equilibrium is restored, the value of K remains the same. But for temperature, the shift will be maintained as long as the system is held at this new temperature. So how does K change? It's directly related to the direction of the shift and what's happening within the mass action expression. If the equilibrium shifts right, then there are more products, which means a larger numerator in the mass action expression, and K will increase. If the equilibrium shifts left, then there are more reactants, which means a larger denominator, and K will decrease. Finally, a few general trends regarding temperature. Think about changing the temperature as adding heat to or removing heat from the equilibrium system. And the first thing you do is write heat on the correct side of the equation. Then determine if heat is added or removed. If the temperature increases, heat is added. If the temperature decreases, heat is removed. Once you have these two parts figured out, then you treat the heat in the same way as you would if you added or removed any other substance. Adding heat will push the equilibrium away from that side, and removing heat will pull the equilibrium toward that side. So the first thing we do is we assess whether the reaction is endothermic or exothermic. We have a positive value of delta H. That tells us that our reaction is endothermic. Endothermic reactions absorb heat, and so we write heat on the reactant side. The next thing we do is take a look at the problem and determine if heat is being added to or removed from the system. The temperature change is from 25 to 85 degrees Celsius. That's an increase in temperature, which means we are adding heat to the system. And when we add heat, we're adding a reactant, so momentarily we have too many reactants, and the equilibrium will shift in order to form more products. So that equilibrium will shift to the right. The next thing we do is we analyze what will happen to the value of K as a result of this equilibrium shift. So because the system shifted to the right, now we have an increase of products. Because we have an increase in products, it means that the numerator of our mass action expression will increase. So we'll have a larger value of the numerator. If we have a larger value of the numerator, then our value of K will increase. Our next example uses the same equilibrium system, only now the temperature is changed from 39 to 0. But we're going to go through all the steps again, because the more often you see them and you work through them, the more automatic these types of problems become. So the first thing we do is we assess our enthalpy, or whatever information we're given about that to determine if the reaction is endothermic or exothermic. We have a positive value of delta H, so that tells us that we have an endothermic reaction. Endothermic reactions absorb heat, and we write heat as a reactant. In this example, there's a decrease in temperature, so that means that we remove heat from the system. So heat is being removed. Because heat is a reactant, if we remove heat, then the equilibrium is going to shift towards reactants to make more reactants. So the temperature change resulted in too few reactants, and the equilibrium will shift in order to form more reactants, and it will shift to the left. The next thing we do is assess what will happen to K. Because the equilibrium shifted left, that means we now have an increase in reactants, and an increase in reactants means we have a larger denominator in the mass action expression. If we have a larger denominator, then that means that the value of Kc or Kp, whichever one we're talking about, the value of K will decrease. In our next example, we're going to apply the same logic that we did in the previous examples. The first thing we're going to do is determine if the reaction is endothermic or exothermic. We're given a value of delta H. It's negative. That tells us that this is an exothermic reaction. Exothermic reactions release heat, and we write the word heat as a product. Please make sure that you don't skip the step of writing the word heat within the reaction, because the logic follows pretty easily once you have that there as part of the reaction. So we have our heat written as a product. We take a look at what happened with the temperature. In this example, the temperature changed from 25 to 10. So there was a decrease in temperature, which means we removed heat. So when we remove heat from the system, at that moment, we have too few products, not enough products. So the equilibrium will shift in order to form more products, and that means it will shift to the right. To determine what happens to K, we need to take a look at the direction of the shift. So because the direction of the shift was to the right, the result of that is an increase in products. An increase in products means we have an increase in the numerator of our mass action expression. And if the numerator is larger, then we'll see an increase in the value of K. And in our last example, we'll go through the same logic. We identify that we have a negative delta H, and that tells us that we have an exothermic reaction. An exothermic reaction releases heat, and so we write the word heat on the product side. We identify what is happening with the heat. Is it being added or removed? This example has an increase in temperature from 0 to 60 degrees Celsius. An increase in temperature means that we are adding heat. If we add heat, heat is shown as a product, then we momentarily have too many products. And the equilibrium will shift in order to form more reactants. So it will shift to the left. The next thing we do is determine what will happen to the value of K. The equilibrium shifted to the left, so that means we're seeing an increase in reactants as a result of that shift. An increase in reactants means we have a larger denominator in the mass action expression. If the denominator is larger, then we will see a decrease in the value of the equilibrium constant.